Hi, this is Robert Bolaños. Welcome to the analysis and design of a Flyback. This is video 25, how to compensate the TL431 slash Opto. Okay. Before I go through this, let me just review last time in the video 24. And this is very critical because it gives you the simulation skills. I use the average model spy simulation, and I showed how you can extract or simulate the output filter, how to get the plot, and then I also showed how to measure and simulate the error app, and you'll get a response like this. And then lastly, how to simulate and measure the gain, and not so much the gain but the frequency response of the Opto. Okay, so those are the two critical. Okay, so if you have that, you haven't seen those videos, see those videos because it's very critical. So we can continue. We're going to go ahead and compensate. And the statement that I want to say here, that the compensation is simple, or it should be simple, and basically it involves canceling the poles of the filters with the zeros in the error app, and canceling the zeros in the output filter with the poles in the error app. Okay, does that make sense? Okay, and if not, this is basically what I'm saying. So these are the two main equations, and this is for a regular flyback, discontinuous flyback. Okay, so these two, this is the output filter, and these are the error amp. Okay, so basically this equation, which is the output filter and your load, that forms a pole. And what you want to do is you want to set the zero to the same frequency as your pole. So basically they're going to cancel out. And this is the output filter with the ESR that's associated with your output filter. Okay, so those two forms a zero, and what you want to do is you want to cancel with a pole. Okay, so basically these are the equivalent. So if you were to derive an equation, these are basically the two main equations that you would need. So if you solve for, you would end up with okay, and these are the two main capacitors that you need to solve, along with the integrator resistor. This is the integrator. RINT is the integrator resistor. I'm sorry, that's R. This should be ESR. Okay, so these are the equations basically that typically we use to design the compensation of a normal flyback converter. Okay, so now there's a little difference here. because now we're using the TL471 and a opto, so there's some slight differences. Okay, so it's not as straightforward as these two equations, but they're still similar enough. Okay, so anyway, slight differences in that you have to take into account the frequency response or the bandwidth of the opto. So basically the output filter has one pole, and this is the equation. Remember, this is the pole. This is this here. Okay. So if you put it in this format, it gives you the frequency. Okay, so this is going to be in units of hertz. Okay, and this looks familiar again. It's this here. Okay, so we have that. So the output filter is going to have a pole and a zero, and it's going to look like this. That's your pole, and then a zero, and the slope of this would be negative 20 dB per decade, and then 0. Okay, so now we have to take into account the opto, and the opto should look something like this. It could even have two poles. It could have a pole here and a second pole, and when you have a pole, you have a negative dB. If you have a second pole following it, then that's negative 40 dB. Okay, so that throws our plant equivalent off a little bit. Okay, or at least we have to be aware of it. Okay, so here is a way of kind of estimating it in a. Let me go ahead and do this, or restart this from scratch, I guess. Okay, so here I have plotted, and let me go ahead and zoom in a little bit. Okay, this is the frequency response of the output filter. Here's the pole, and there's the zero. Okay, and this is basically what the circuit looks like. Okay, and then the opto is going to be the opto. If you notice, it has about 10 dB a gain, and then if you notice, it goes upward, has a little hump, but then right here it starts turning down. So this is a pole, so I'll put a P here, and then it has a slope, and the slope is negative 20. And then if you notice, this slope is different from this slope. Okay, so that means there's a second pole here. So now from here to here, it's got a negative 40 dB per decade. Okay. Okay. So now that we have both, we can draw these lines, these vertical lines, at where we have a pole and a zero. So we have one right here. We have one here, and we have, this is a double zero. Okay, and then here's one, another pole, a pole here and nothing here. Okay. So wherever we have a pole or a zero, basically most of the poles, we draw a line. And now what we try to do is we algebraically add the slopes. Okay. In other words, we're going to predict or try to predict if we were to add the frequency response of your output filter and the response of your opto, they should total a dominant or a total response. And that's what we're going to do. Okay. So, we'll go ahead and clean this up a little bit. Oh, messed up there. See if I can draw that again. Okay. So, let's go ahead and do that. I'm going to go ahead and use red. So here, this is a slope of 0 because it's horizontal. It's not changing. Okay. And if you were to add, basically you're adding these sections, this interval, with this interval. Okay. And since it's 0 plus 0, you get a 0 slope as well. Okay. Now here, from this interval, we're going to add this and add it to this. And we're going to assume that this is straight, although it does have a slight, there's actually a pole 0 here, but they're so close that they're canceling. But we're going to go ahead and assume that this is also 0. So a negative 20 plus a 0 equals a negative 20. So then you draw a slope. And then this is negative 20 dB slope. Okay, so now we go to the next interval. We're going to go from this interval. And since this is 16.7 and 32, they're really close to each other, so we're just going to go ahead and neglect this one, or just say that they're the same. So we're going to add this interval, and we say that this is 0 dB, and this is negative 20. So 0 plus negative 20 is negative 20. Okay, so we got there. So now we're going to add this interval. This is 0 dB. And this here is negative 40 dB. You've noticed the slope of this is steeper than this slope. So 0 plus a negative 40. So you draw this with a slightly steeper. So this would be negative 20, negative 40. And then the last is here. This interval from here to here. This is positive. 40 has got an upper slope. This is a negative slope. So they cancel each other. So a positive 40 and a negative 40, you get Okay, so this is important because this is what you're going to compensate. This is what you need. So this is your output filter and the opto. Okay, so let's go ahead and see if we can get this simulation, this filter, and see if we can duplicate, or at least see if we get some resemblance. Okay, now to measure that, we are interested in seeing the output filter and the bandwidth of the opto. So in this case, we move this to this right there. That would be the cathode of the LED. So if you put the in here and leave the out here, you should get that result, hopefully. Okay, so now if you notice, let me go ahead and delete this, the amplitude, and let me cut the frequency. I think the frequency we went up was, this is 1 meg, so let me redo this to change the scaling to 10 instead of 100. Okay, so if you notice, see if we can put this together. See if they resemble. Okay, so if you notice, it's a pretty good resemblance in that you have this flat top, okay, and then you have this long period of negative 20 dB, and let's measure that. We can measure that as well. And I know that on some of these simulations, when I do them in black, they don't come out very well, so let me do that. Okay, so now we're going to measure the delta, and it's 1 dB. I'm sorry, it's 20 dB per decade. So this is 1 decade apart, and if you look in here, it's 18, so it's close to 20. So this is showing that this has a slope of 20. Okay, now this one is a little harder to measure, so we'll put this one here. This one is not quite a slope. Let's see. What the slope would be. Nope. Actually, this does not have that. We don't have enough x-axis to measure, but this is much steeper, and hopefully you'll take my word. This is a 40 dB per decade. So basically, should look like this part. So this part should look like this part, and then this part should look like that part. Okay, so basically this is where we want. This is the waveform that we're looking at. Okay, so now how do you compensate? What is it that you want to do? Okay, so the number one thing is you want to look at the first pole. Remember, this has one pole, and then there's a second pole, and there's 2 zeros here. So to measure the frequency, we measure the delta y, and we move this and we look at this here. We look at the y2 minus y1, and once we measure a -3, that's our point. So this is close to right there, just above. So it's 200, about 218. So let me go ahead and put that 218, 218, 218 hertz. Okay. So then the next one point of interest that you want to be sure you can measure where, and this is a little harder to measure, so you kind of have to guesstimate. So one way is using the graph paper. You would draw a line through this, and then you would draw a line through this slope, and where they intercept, that would be the point. So in this case, what I'm going to go ahead and do is I'm going to go ahead and kind of estimate it. And just say that's probably in the in-between. So this is close to 87 kilohertz. Okay, and then the next is of course this frequency, and this would be 549. Okay. Maybe just say 600. Okay, so now we have the placement of our. Actually, let me remeasure that just to make sure that I'm at the right place. Redraw this, be sure. Actually, the frequency is a little higher than I expected. Okay, it looks like it's 436. We got a delta of 3. So let me change this. Yeah, because this is a kilohertz. This is 2, 3, so it's closer to 3. So it's actually 436. 436. 436. 36. Okay, so let me go ahead and see if I can copy this. Okay, so I have that. Okay, so now, what we're gonna do is we're gonna go ahead and cancel this uh, pole, and since we already know the frequency of when it appears, let's find the time constant. Okay, so to find the time constant, what we're going to do is 1 divided by 2 pi, which is 6.28, times 438 hertz. We divide it or evaluate it. Okay, so now we have that. So this is the time constant. So now we calculate what value of capacitor I need here to cancel that pole. So now with the time constant, all I have to do is divide by my integrator resistor. So if I divide this by 10,000, it should give me the amount of capacitance that I need to cancel that pole. And I need 36.3 nano. Okay, so now I'm going to go ahead and bring this back here, and then I'll take a look and see if I was able to cancel it. And it did. See, it canceled it. And as a matter of fact, you can see that the loop already looks pretty good. Okay, just by doing that. Okay, so let's see how it would look if we had, let's say, a 3 nano. See, it would look like that. Say it doesn't have a cancellation. Actually, you can see the pole right here. Okay, let's make it even smaller. Say you can see the pole right here, and you can see the output filter. Okay, so again, this is where we're going to cancel, and this basically proves that if we put a 33, at least close to that, 36 should be close enough that will cancel that. Okay, so now we're gonna do a little bit of hand waving, and I'm gonna follow what most the power supply community says, that we're gonna go ahead, since we're using this system, since this is, we already calculated, or at least through the simulation, was 436 hertz. This is the pole. Okay, now we want to set or cancel the 0. Okay, so what we want to do is we're going to set it to half the switching frequency. So since this power supply is going to be switching at 100 kilohertz, we're going to set our pole in the error amp to 50 kilohertz. Okay, so Again, we'll do this. Okay, we're gonna set it so it's 1 divided by 6.28, which is 2 pi, times 50 kilohertz, close parentheses. That's the time constant. And now we're going to divide it by 10,000. And this is the compensation. So that would be 11, 12. So this would be at 300. I think it was at 318. Yeah, 318 picofarads. Okay, and I'm gonna go ahead and save that and see what the difference is. I didn't have a resistor or a compensator roll off, so I'll add that, simulate it, see how it looks. That looks pretty good. So if you notice, it looks like right there it's got a little slope there. That's where it's kicking in. Okay, so now the important part is here. We can disregard all of this. So let's go ahead and move this to the other side. Change this to, okay. So this is our compensated loop. Okay, so now we're going to see where it crosses over and where the amplitude crosses over to 0 dB, which is about 5.7 kilohertz. Okay, then where it crosses and you look at the gain, that would be your phase margin. Phase 292 degrees, which is pretty stable. Okay, so now we do this. We'll move the phase cursor to where it crosses the 0 dB, and then we measure the gain, and this is called the gain margin. And gain margin is -32. Oh. Not sure what I did that changed it. Okay. That would be down here, and then let me re-add this again. Thought it was -32 dBs. dB right there. Okay, so anyway, that's a good compensation. Looks very a very stable system. So basically that's how you compensate. You need to do these manipulation with the spice and then be able to draw this, or at least you don't have to draw it, but let the simulator do it for you, but at least have an understanding of what is happening. And once you know or have a feeling of what is actually happening, then the composition is actually trivial, or it's not as complicated as one would think. Okay, so I'm gonna go ahead and stop here. On the next video, what I'm gonna do is I'm gonna compare, or I'm gonna validate this model. Okay, this is a average model. I'm using Jack's model that he developed, and I want to validate it. And how am I going to validate it? Well, we're going to do a switching model, and we're going to compare it with the switching model and see if this model is correct or not, or if it's accurate enough. Okay, I think that should be good enough. Hopefully this will get some of you guys caught up when some of your